Having done first problem on source conversion, we will do another problem of source conversion. As the problem says, convert the given combination of sources into a single current source. As you can see, this is a problem wherein the quantities have been in phasor form. The various quantities that have been mentioned here, they are in phasor form. I suppose you can easily see the various things. Between A and B, we can easily identify three sources. Okay, there is one voltage source of, let us say, we will try to call this V1 for easy understanding, and let this voltage source be V2, and let this current source be I. Alright, so we are easily able to identify that a voltage source V1 has got an impedance of 5 at an angle 45 ohms in series. Its impedance, its internal impedance. V2, which has a magnitude of 10 at an angle minus 90 volt, has got a 2 ohm impedance in series. Similarly, we can see that the current source I has a magnitude of 2 at an angle 90 amperes, and of course its internal impedance comes in parallel with it, and that is J2 ohms. What are we expected to do? We are expected to convert this entire combination into a single current source. You have to remember this, into a single current source. How will a current source look? This is how a current source looks. This is a current source. This is a current source. Okay? This current source has got an arrow either up or down depending upon the polarity. Now I'll simply show the upward arrow. Okay? This is its internal impedance. This is the current IS. Let us say this is the internal impedance of the source. This is our current source. And the figure here, this is our voltage source. What is this voltage source? This is Vs, has simply shown an arbitrary polarity, and this is we will call it ZV and ZI. That would be better. That would be better. The internal impedance, we will call it as ZI. Alright? So this is the current source, this is the voltage source. I've just drawn here for our future reference. Alright? So what we have to do is, we have to convert the given figure, which is our figure 1, into the figure 2 format. In this manner, we have to reduce it to figure 2. If figure 1 can be written as figure 2, then what is the value of IS and what is the value of ZI? That is what is being asked. Alright, now how to do this problem? As you can see, this entire setup, if you can see, between the terminals A and B, if you view the network between the terminals A and B, how the circuit appears. We can see that this V1 source is one independent quantity, whereas we can see V2 and I, the source V2 and the source I, they are in parallel. And between A and B, if we see, these two parallel sources, when converted to a single equivalent, will come in series with V1. Alright? So, this network is viewed like this, in this manner. Now, how do we reduce? If we have to reduce the network, our first step would be to convert this parallel combination of V2 and I into one single source. Alright, and that single source will come in series with V1. So obviously that single source should be in voltage source format. Alright, that is our understanding. Now, if you internally see what is there within this yellow boundary, is that V2 and I are in parallel. So the conversion of sources in parallel is convenient if both the sources are in current source. Alright, so what is our step 1? It's very clear that V2 source having an internal resistance of 2 ohms has to be converted to a current source. That is going to be the first step. All right. Now we will try to proceed with the conversion. Okay. I will write the conversion. Okay. So at step 1, I'll take my white pencil to do the computation. At step 1, we will try to convert source. What source is that? Voltage source V2 into its equivalent current source and rewriting the network we get the following figure. All right. So we have to write V1 as it is. We have to convert V2 into its equivalent current source and I as it is. Okay. So I will try to write the network now. So to write the network, I'll make use of this because I have written one source. This I will copy. I will take it here. I'll paste it. I have pasted one voltage source. That is as it is. I'll put the magnitudes. Okay. And I will take this current source. I will only copy this much. How much? I will not copy that little. I will not want that. What I want is only this much. This much I will. Okay. This I'll copy. I will take it here and paste. I'll take it here, another one, paste. Okay, now we require this much. Okay, so what I further do is I'll try to erase these things. I'll try to remove these things. I will try to remove this also, and I'll try to put the figures back. So this diagram, this source comes little here. Okay, I will connect it. Then I'll connect the source. I'm just trying to draw the diagram. That's all I'm trying to do. So drawing the diagram would take time. So what I've done is I have just taken these values. I will now insert the values. What do? I will take this red only. Okay. So my first source is V1. I will try to write as it is. That is 5 at an angle 45. This is 5 at an angle 45. All right. Then this is 10 at an angle 0. I will write V1 equal to 10 at an angle 0. Then I will write as I as it is. This I is 2 at an angle 90, upward arrow, 2 at an angle 90. This is so many amperes, and its internal impedance is J2. This also I will write it as it is. Now what I have to do is convert V to its equivalent current source. What is that current source equal to? The magnitude of this, I will call it, let us say, is I2. I will compute it here for you. I2, the magnitude of this current source is V2 divided by its internal impedance, that is 2 volts. So this is 10 at an angle minus 90 divided by 2. It's a very, very simple computation. 2 can also be treated as 2 at an angle 0. So with calculator and without calculator, you can even easily do it as minus. All right. So the direction of the arrow should be taken into consideration. If you see the sign of the V2, lower end is positive. So my current source I2 will have the arrowhead pointing downwards. All right. So the magnitude of I2 I have found to be 5 at an angle minus 90, so many amperes. All right. So I2 will have an internal impedance equal to the same 2 ohms, but it is in parallel. This is 2 ohms. All right. Now we have written the equivalent. We have written the equivalent source, and this is my A and this is my B. This is A, this is B. Now what's my next step? Now I can easily see the source current I. This we have called it as I. This is my I. This is I equal to. Now in this network, in this particular figure, I and I2 are in parallel. There are two current sources which are in parallel, but they are of opposite polarity. What do we mean by polarity in AC circuit? When we talk about an alternating current circuit, or when we are talking about phasor quantities, the sign always indicates what we call as instantaneous polarity. This is a side note you have to remember. Instantaneous polarity, what is that supposed to mean? When the source I has got upper end to be positive, at the same instant of time, I2 source has the lower end being positive. Okay, it is instantaneous at that particular instant. Now, if I want to add the two, how do? I take the difference of the two sources. All right, I take the difference of the sources because one is at the upward direction, the other current at the same time will flow in the downward direction. So I can combine the two current sources and rewrite the circuit. Okay, step 2. I will write step 2 in the same white color. My step number 2, okay, converting the two current sources. What are the two current sources? That is I, I2 into a single source and rewriting the network. We will try to rewrite the network. What do we get? I may have to rewrite the network now. How will the rewritten network is going to be? I will try to take the same sources. So this is for my easy, writing of the diagram. I have drawn these sources so that I can take this I'll copy, I'll put it here and paste. I'll take this current source also and I will paste. This is for my convenience. I have done this thing. Let's see if I can do this. Second, I'll copy and paste. Yeah, that's good. I will erase this. I'll erase this also. Okay, all right. So what I'm trying to do now is I have converted that source into one single current source. This I will do. Okay. So this is my A and this is my B, and I will try to convert. This is my A, this is my B. Okay. So the source as it is, we have, I think we have called it V1, right? That's V1. Okay. V1 equal to 10 angle 0 volt, and this internal impedance is 5 at an angle 45. This we haven't done anything right now. We are maintaining V1 as it is. Now what is the magnitude of this current source? Earlier it was my I2. Now I'll call this I3. What is this I3 equal to? How do we do? I3 equal to, and I'll take now. Therefore, I3 equal to, how do we compute I3? I3 can be easily computed as 5 at an angle 90 minus 2 at an angle 90. Alright. 5 at an angle minus 90, right? Yeah, it's 5 at an, so I have to be careful with the signs. Okay, this is equal to, if I can do with the calculator, I will get it to be 3 at an angle minus 90. Okay, so many amperes. I am able to get I3. And I'll call this impedance, let us say, as Z3. And what is that Z3 equal to? How do I do? What is Z3 equal to? Z3, if you look at the previous diagram, is a parallel combination of this 2 ohm and this J2 ohm. It is a parallel of these two. Okay? So we need to do that. So Z3 equal to parallel combination of 2 parallel J2. How do we do? If two impedances are connected in parallel, their equivalent is the product of the two divided by the sum of the two. That is 2 ohm into J2 divided by 2 plus J2. It is preferable you use brackets while doing it in calculator. Otherwise, sometimes you may end up incorrect results. So try to use parentheses. Alright. So my Z3, if I can compute, I will get as 1 plus J. This is in rectangular form. The same thing is also equal to 1.414 at an angle 45 degrees. Yes. So this is Z3. So I'll put back the value of Z3 in my network. I have found Z3 to be equal to 1.414 at an angle 45 degrees. So many ohms. Now, okay, so we have reduced the network to this figure. It is fairly simple now. Now how do we see? Now it's very simple. Now my I3 is 3 at an angle minus 90. So many amperes. I put an upward arrow. I'm sorry, I should have put a downward arrow, not an upward arrow. So here again, this has to be cleared. Because I copied the source, and that source I had marked an upward arrow. So this is the direction of the arrow. Instantaneous polarity is like this. Now, what further can be done? Common sense will tell us. We have done so many problems, and the practice tells us that, what does it say? This current source has to be converted to its equivalent voltage source, so that V1 comes in series with the new source that we are going to get after conversion, and we can combine the two. Voltages in series get added. So when you have to convert sources in series, you have to have the sources in voltage source form. Okay, equivalent source should be in voltage source form. Then it is easy to add up. Alright, so we will go with the next step. Step number, I suppose, is step number 3. We are at step number 3. What do we do? Step number 3. Step 3 is, now we will try to converting I3 source into its equivalent current source and rewriting the network. What do we get? Sorry with that. Sometimes this pencil gives little trouble. Rewriting this network, what do we get? We get the following network. What do we do? I will pick up the voltage sources because that is easy for me. I need not draw it all over again. I will take this. I'll copy this. I will take it here. Paste. I'll take one more and paste. So I require two sources, right? So two voltage sources. What I do is I'll try to connect the two sources and I will get rid of this thing I'll get rid of this sign also, this sign also, this sign also. Okay, that should be okay. Now can I erase this much? Yeah, this is beautiful. All right, now I'll try to pull out the wire a little longer so that it becomes clear. Now this is my A and B. Okay, now what have I done? Now I am trying to convert I3 into a source, a voltage source. All right, so I will call that, this is my V3. I'll call this V3. I'll call this V3 and let this 3, this is Z3. This is my, as usual, V1, which I already have, 10 at an angle 0. I haven't done anything. There is a positive polarity at the top. This impedance I have not bothered to change. It is as it is, 5 at an angle 45. These two things are retained. Now I have to get V3 and Z3. How do I get V3 and Z3? So V3 is equal to, I'll take my pencil in white color. Now my V3 is simply I3 into Z3. V equal to IZ. It is that simple. V equal to I into Z. Alright, so this comes out to be I3 into Z3. So I3 is 3 at an angle minus 90. Z3 is whichever format you can have. It is 1.414 polar or rectangular. Whichever form. Your calculator these days is pretty smart. You give the quantities either in polar or rectangular. The computation is carried out quite comfortably, quite easily. Alright, so we have to compute this. This will come out to be equal to my V3. If I can do this computation, this will come out to be equal to 4.24 at an angle minus 45. I mean, normally most of the calculators give the result in rectangular, right? So I will write it in rectangular first. So the rectangular form, you will get it as 3 minus J3 volt. This on conversion to polar, you will get it as 4.24 at an angle minus 45. Okay, that is my V3. So I'll put my value of V3 in the network. So V3 is 4.24. You have to be careful with the calculations. 4.24 minus 45, and Z3 is the same impedance. This is the impedance. That is 1.414 at an angle 45. Okay, so many ohms. These are all volts, these are all in ohms. What is the polarity of V3? So if you look at I3, I3 has got an arrow downwards. So the downward end is positive. All right. Is it okay? So now if we can take, now we are able to get the given network as a series combination of two voltage sources. It is simple enough. All we have to do is we have to add these two sources. Okay, taking polarity into consideration. All right. So if you take polarity into consideration, how do we exactly do? Now the next step is simple. What does the next step state? It's very, very simple. Step number 4 is adding or combining, adding say, we will try to do, we'll put combining, it will be better, that word is better. Combining the two voltage sources. What are the two voltage sources? V1 and V3. We get, what do we get? We get the following figure. That's what we mean. Okay, we will try to write the figure. Okay, I will pick up the voltage source again. The reason of drawing the voltage source is just to do this business. I'll copy this source so that I can save time on drawing the network. That is the idea. That's all. Okay. Now what I have done is I have taken the two voltage source equivalent. I have drawn that source. Okay. I'll try to now do the conversion. I take this little far. This is far. Okay. Now this source, I will have to find out what is the magnitude of this source. What do we call? Have we called voltage source anywhere V? We have not called anywhere the voltage source to be V. So I'll now make this V. What I mean is this is my V. I'll call this V and I'll call this Z. Okay. So what is the value of V? What is the value of Z? And what is the polarity of Z? I mean, what is the value of polarity of V? That we have to determine. What is that V equal to? So V equal to, if I start from B, go towards A in this figure. In which figure? In this particular figure. This is figure 1. I'll rename the figure so that I can refer to them. This is my figure 2. Okay, and this is my third figure number 3. This is my figure number 4. This is figure 4. And this is figure 5. Okay. So in figure 4, if I start from B, go to A, I will come across positive to negative in V3, which is supposed to be an instantaneous drop voltage drop. Then I go via Z3 and come up to V1. V1 if I see, I'll hit negative sign, then go to positive. That means gain in voltage. Negative to positive is gain in voltage. So if I go from B to A, I will have to compute V as equal to V3 minus V1 with the polarity of V3. It is lower and positive. That is going to be V. Alright, so we will try to substitute these two quantities and compute. What is my V3? V3, I have got it to be, okay, V3 is equal to 4.24 at an angle minus 45, at an angle minus 45, minus the other source is 10 at an angle 0. Alright, this is equal to this computation. I'll enclose them in bracket. Let us have this practice of putting the values in parentheses. Now this comes out to be equal to minus 7 minus J3. You will get it like this. This on conversion to polar, you can write it as 7.167 at an angle minus 156.8. That is my V. Okay. So what is my Z equal to? How do I compute Z? Z is simply the sum of the two impedances. Alright. The two impedances Z equal to the impedance Z3 plus Z. Because those two impedances are in series. Z3, and I have called it as Z1 rather. This is my Z1 equal to. So what I'll do is I will have to add the two. Okay. If you look at figure 4, Z1 and Z3, there are two impedances in series. From B to A, they are in series. Alright. So we may have to add Z3 and Z1. So this comes out to be equal to Z3 is what? Z3, where is my Z3? Z3 is 1 plus J. 1 plus J. Is it 1 plus J? No. Z3 is 1.414 at an angle 45. Sorry. Yeah, it is as good as 1 plus J in what do you call that? In polar form. In rectangular form, it is 1 plus J. I will not use this so that you should not get confused. I'll take this value only. This is 1.414 at an angle 45. Okay, this is Z3 plus 5 at an angle 45. Okay, so this Z comes out to be equal to 4.535 plus J 4.535. This in polar form, if you convert, you will get it as 4 at an angle 45. So many ohms. So this is my Z, this is my V. Okay, this thing is V, this thing is Z. So I will have to put these values in the figure. So V, I'm getting it as, okay, I'll put 7.617 at an angle minus 156.8 V. Then the Z equal to 6.414 at an angle 45. So many ohms. All right. And this is my A, this is my B. Now what do I do further? The problem says you have to convert it into an equivalent current source. Now figure 5 gives me the equivalent in voltage source, but we are interested, the problem says you want to have it in current source, right? So single equivalent current source. So we have to get an equivalent current source. What do I do for that? I will pick up this current source, which I have kept it ready for my immediate use. I'll copy this diagram, take it back, take it down, paste it here, and call this figure. I'll shift it here. Okay, this is my figure 6. And I will get rid of this arrow also. Now I will write the step, the last step. What do we call that? That is step number 5. Step number 5. This is my V and Z. Okay. Step number 5. Converting the above voltage source into its equivalent current source, we get what? What we will call this? Should we call it I? Where we have used I and ZI. Okay. So if you look at figure 5, the lower end of the voltage source is positive. That means my current source should have an arrowhead which is pointing downwards. This is my A, this is my B. Now I have to compute the values. How do I do? Now simple. I is equal to V by Z. Okay, you have found V. V to be equal to whichever format you can take, whichever polar or rectangular. I will take polar here, minus 156.8 divided by the impedance is 6.414 at an angle 45. So this on computation will give 1.187 at an angle 158.2 . Okay, so many amperes, and my impedance ZI will be equal to the same as Z, 6.414 at an angle 45. So many ohms. That would complete the problem. All I have to do is put these values in the network, and this is equal to I equal to 1.187 at an angle 158.2. So many amperes. ZI is simple. It is same as 6.414 at an angle 45 so many ohms. Okay, this completes the problem of converting the given network into a current source. Don't mind the shape, but then figure 6 gives the equivalent current source. So that's all. It is simple. You may have to identify the network properly and then see. Okay, a quick recap, we'll see. We'll see a quick recap. We are supposed to convert the given source into an equivalent current source. So what we have done is, this you need not write. What I mean to say is, whenever you do it, this part you need not write. I have written it here because I want to use these figures, so that drawing of figures is little easy for me and I can do it quickly. So you need not do this. Alright, so this is not for you to bother. So all you have to do is, so given network, you have to first look at the network, identify the network. You can see it as this V2 and this I, they are in parallel. So to convert it into an equivalent source, you have to have both the sources in current source. So you will convert V2 into a current source. You are able to get two current sources in parallel. So reduce them into a single source by adding it up. Then now it is a series combination of current source and voltage source. To convert series combination or to reduce series combination, convert the current source to voltage source. That's what you've done it in step 3. Then you have to combine the two. Step 4 will give you one equivalent voltage source, but the answer that is expected is in current source. So you convert that voltage source into a current source. You have to be little careful with vectors in computation, feeding it in calculator and do it properly. You have to be little careful in copying values from one figure to another, one formula to another, pressing the values. You have to be careful in computation. Otherwise, they are all simple things. Alright? Hope this video is clear to you. This problem is clear to you. And I suppose I will stop here. In case I get more problems or problems from your side, I'll be able to solve and give you the results, give you the solution. Okay? Thank you.